Alright, so this will be the first of 3 videos on continuity, which is the last topic that we need to cover in the chapter on limits for Math 1560 at U of L for fall 2017. So we'll dive right in with the definition. So what does it mean for a function to be continuous? So continuity is something that we sort of take for granted, and it's one of these things where at first you might wonder, why do you bother to make a definition? Because every function that we deal with, and we'll see this in a bit, all the functions that we're used to are continuous functions. They all have this property. Of course, there are functions that don't have this property, which is why we have the definition. So what does it mean to be continuous? So a function is continuous at a point. So right now we're talking about continuity at a particular point. So we have this point C that we're interested in here, and we want to say that a function is continuous at C. So what do we mean when we say that f is continuous at C? We mean that the limit of the function at that point, so here's the limit, x approaching C, right? This is the point we're interested in. The limit of the function at that point is equal to the value of the function at that point. And remember that these are two different things. The limit value has to do with values of the function when x is near C but not at C. In the definition of the limit, we don't actually allow x to equal C, so we're near that point, but we don't actually reach it in the limit. On the other side, though, we're saying exactly what happens when you do reach that point. When x is exactly C at that one single point, what is the value of the function? So continuity is the requirement that these two agree, that the limit value equals the function value. And there are a couple of things, of course, that you need to make this definition work. One is, well, the limit actually exists, right? So the limit as x goes to C of f of x exists. In particular, and this is important if you're trying to construct piecewise functions that are continuous, the left-hand limit needs to equal the right-hand limit. Okay, and the limit also, it also needs to be finite, right? Because the function value can't be infinite. It doesn't make sense to say that f of c equals infinity. That's not a reasonable output from a function. So when we say the limit exists, we mean it equals some finite value L, right? Now, of course, both sides of the equation have to make sense. So f of c has to be defined. So in other words, c belongs to the domain of f, right? So c has to be in the domain. If f of c is undefined, then you don't have a continuous function. Okay. So for example, if you were doing something like f of x equals okay. Here's maybe a very basic example, almost a silly example. X squared minus 1 over x minus 1. Now for all values of x other than 1, you can factor the top and you can cancel, and you're just left with x plus 1 when x is not equal to 1. But you can't actually plug in x equals 1, so 1 is not in the domain. And if you were to plot this thing, you would have a straight line, right? And there would be a hole in the graph at x equals 1, right? So the limit exists. There's nothing wrong with the limit. You can take the limit as x approaches 1, and you find that the limiting value is 2. But f of 1 is undefined, and so that function has a discontinuity. There's a break in the graph, right? The intuitive notion of continuity is that you can draw the graph without having to pick your pen up off the page. So the graph is one solid piece. There are no breaks or jumps or anything like that in the graph. So you need the limit to exist, you need the function to be defined, and then of course you need to make sure that 1 and 2 actually agree. So the limit value has to agree with the function value. So if I define this thing piecewise and I decided to say, okay, f is not defined at 1, and then I define f of 1, but I define it in some silly way. I put the value down here. I say f of 1 is going to be equal to 1 rather than 2. I still don't have a continuous function, even though the limit exists. The limit exists and is equal to 1. F is defined at 1. F of 1 would be equal to 1. But those two are different values, and so again, you have a discontinuity. And we'll see there are a number of different ways that things can go wrong. Okay. All right. So here's an example, basic piecewise function, and we want to look for any places where the function fails to be continuous. So how can we identify points of discontinuity? Well, one of the things that we'll see is that polynomial functions are always continuous, right? So the x squared we never have to worry about, right? Because we notice that and let's just kind of do this as an example, right? Just simple properties of limits would say that if I'm considering a value of a bigger than -1, and I take the limit as x approaches -1 of f of x, I'd be taking the limit as x approaches, a, right? Not -1, but a. A is bigger than -1. Well, properties of limits tell us that anytime you're taking the limit of a square, that's the square of the limits, and we know that the limit of x as x approaches a is a, so we get a squared, which is f of a, if a is bigger than -1. So we have continuity for all values of x bigger than -1. What about if x is smaller than -1? Well, so if I'm looking at a point where a is less than -1, and I consider the limit as x approaches a. So now I'm looking at the limit as x approaches a of 1 over x plus a. And, well, again, algebraic properties of limits tell me that I can take, say, the limit of a quotient is the quotient of the limits, and of course it's a constant on top. The limit of 1 is just 1. And so I can do that. Oops, sorry, not a there. 2, x plus 2, right? X plus 2, and so then this is what? Well, this is equal to 1 over a plus 2, except that limit rule for quotients only works if we know that the function in the denominator is going to a non-zero limit, and so this is f of a, but I need to make sure that a is not equal to -2, right? Notice that -2 is not in the domain of that function. And so that gives me my first point of discontinuity, right? I know that one of the points where my function is not continuous is when a equals -2, because I have a discontinuity there. I have a place where the function is undefined, right? So f of -2 is undefined. I need the function to be defined to have a continuous function. So I have a discontinuity there. Now the other place, of course, where things could go wrong is when a is equal to -1. So what happens when we approach -1? Well, as we approach -1, we have to consider one-sided limits, right? And if I let x approach -1 from the left, well, remember that approaching from the left means that I'm considering values of x that are less than -1, and if x is less than -1, then I'm in this situation here, so I have to use this function. So I plug -1 into there, and I get 1 over -1 plus 2, I get 1. Okay? If I approach from the right, -1 from the right, so remember that what this means that x is bigger than 1, and that means that we're in this situation here when x is approaching from the right. And if x is approaching from the right, that means I got to use x squared, so I get -1 squared, which is also 1. And so in fact, I only have one point of discontinuity, this vertical asymptote at -2, where I have this infinite limit. That's actually the only point of discontinuity. Why? Well, notice that at minus 1, the limit as x approaches minus 1, well, the left-hand limit equals the right-hand limit, and so that gives me the overall limit of 1, and that is also equal to f of minus 1, because notice the equals here and the less than or equals says that, okay, when x is actually equal to minus 1, I should use x squared to compute the function. Minus 1 squared is 1. Things agree, so it's actually continuous there. So the only point of discontinuity is that gap in the domain at minus 2. All right, moving right along. We want to now go from defining continuity at a point to continuity on an interval. Open intervals are easy, so we would say that a function f is continuous on AB if f is continuous at C for every single point in the interval, for all C between A and B. That's simple enough, right? So continuity on an open interval just means continuity at every point in the interval. And you could, if you wanted to, you could extend this to intervals like, you know, A to infinity, or minus infinity to B, or minus infinity to infinity. Any kind of interval like that, the same sort of story works. What about closed intervals? Well, there you have to be a little bit more careful. So we would say that f is continuous on a closed interval from A to B if, well, one of the points you're going to need is that f is continuous on the corresponding open interval, so on the inside. But then you also say something about the endpoints. What do I need to say about the endpoints? Well, the problem with the endpoints is this closed interval might be the domain for my function, and so I can't necessarily consider limits at the endpoints, right? Because I don't know if f is defined for x less than a or bigger than b. So at the endpoints, I can only consider a right-hand limit at the left endpoint and a left-hand limit at the right endpoint. So I need to have this. I need to have that the limit as x approaches a from the right equals f of a, and I need to know that the limit as x approaches b from the left is equal to f of b. So I have to put those conditions in. So that's something that you have to watch out for. Sometimes we might, in these latter conditions, we might say that the function is continuous from the right at A and continuous from the left at B, just kind of extending this idea of left and right hand limits. And again, you could also consider, you know, intervals involving infinity where you include the other endpoint. You would make a similar definition there. Okay, so we know what it means to be continuous at a point. We know what it means to be continuous on an interval. And now we can kind of look at a standard question, which is if somebody hands you a function, you want to know where it's continuous. So we kind of already dealt with this in that earlier example, and we're skipping ahead a little bit here because we need a few properties. That's coming up in the next video. But we can ask for the intervals on which a function is continuous, right? So we want to kind of answer generally, what are all the places where my function happens to be continuous? Well, for this first one, notice that this first function, if I factor the bottom, I've got x over x minus 1 squared. And we know, using limit laws, we know that we can take the limit of the top divided by the limit of the bottom, and so we know that for x not equal to 1, we don't want x equal to 1 because then we divide by 0. We would know that the limit as x approaches a of f of x Well, it's going to be a over a minus 1 squared. I guess I should say maybe not x but a here, which is the same thing as f of a, right? So when I skipped some steps with that limit, but if you were doing the limit, of course, you would do the limit of the top over the limit of the bottom. The limit for x, we know that's just a. For the bottom, we know we can bring the limit inside the square, and again, x approaches a. So we see that it works there, but of course we know that the function is not defined at 1, right? So 1 doesn't belong to the domain, or we could simply say that, we could say that f of 1 is undefined, and so that means that f, is continuous everywhere else. So in interval notation, we could say that it's continuous from minus infinity up to 1, union everything from 1 up to infinity. Okay. What about the next one? Well, again, continuity here boils down to really a domain question, because if we were taking the limit, again, limit properties say that, okay, I've got 1 over a function, so if I was taking the limit of g of x, it would be 1 over the limit of this square root on the bottom. We've also seen examples showing us that we could bring the limit inside the square root, and then we know how to deal with the limit of 1 minus x squared, right? And so we know that basically, with a little bit of work, we can see that for any a in the domain of g, we know that the limit as x approaches a of g of x will be equal to g of a, so we have continuity. So this boils down to determining the domain. So what is the domain? We need to make sure that 1 minus x squared is bigger than 0, right? It has to be bigger than 0 because I can't take the square root of a negative number, and it can't equal 0 because I can't divide by 0. And so that means that x squared has to be a number that is smaller than 1. We could work out this inequality, or you can kind of think it through. But the punchline here is that x is going to have to be a number between minus 1 and plus 1 in order for 1 minus x squared to be positive. Alright, so that's it for the definition. In the next video, we're going to look at some of the properties of continuous functions.